Hi students, this is Mr. Epperson, and this video is on molecular polarity. In this video you'll be able to determine if a molecule is polar based on the types of bonds the molecule has and the molecule's shape. To review from last time, we talked a little bit about electronegativity and discussed how electronegativity can be used to understand how electrons are going to be attracted to particular parts of an atomic elements in an atomic bond. So for instance, because the electronegativity of chlorine is higher than that of hydrogen, more of the electrons are going to be centralized around chlorine in a hydrogen-chlorine bond than around hydrogen. And this causes what's called polarity. And polarity basically means that there's a pole, a north and a south, but instead of saying north and south, we just have positive and minus. We figure out how the polarity will be affected and basically the degree or the size of polarity by doing a little math. We just take one element in the bond, for this example down here, carbon and hydrogen, and we find their values in the periodic table by looking at an electronegativity periodic table and then subtracting them from each other and seeing what the difference is. If that difference is greater than 0.5, then we say that it is going to be a polar bond. If it's less than 0.5, we call it a non-polar bond. We're also assuming that we're dealing with non-metals in these relationships, unless we're talking about an ionic bond, which we have down here. But the non-metals are the only atoms that are capable of forming a covalent bond, and so we're just assuming that we're dealing with non-metals. So, and we're also not dealing with the noble gases, and we have to include hydrogen in there. So those are the only atoms that we're considering here, and we're just seeing how do the two atoms relate when they bond, and what's the total value going to be. I also want to quickly go over the difference between a bond and a molecule. A bond can always represent a whole molecule, but it's certainly always a part of a molecule. So what I mean is there's a molecule here shown, carbon tetrachloride. This molecule has 4 chlorine atoms around it and a carbon in the center. So because it is rather large, it obviously has more than just one bond in it. It has 4 bonds that all connect to carbon, and it has 5 atoms. This molecule down here is oxygen, and it is the smallest, one of the smallest molecules you can have because it only has 2 atoms in it. So within those different types of molecules, you have a different number of bonds that you can make, but that's important to know because bond polarity is not necessarily the same as molecular polarity. And that's what we're studying today, is a whole molecule's polarity, not just the polarity of an individual bond within a molecule. Now, when you're dealing with a molecule that's 2 atoms big, you're basically just dealing with the polarity of a bond. So you'll only need to look at the polarity of the bond to see what the polarity of the molecule is. We're going to see it's going to get more complicated if you add more than 2 atoms. While we're looking at that bond, we can also determine whether it's polar or nonpolar based on whether it has a electronegativity difference less than 0.5, we're going to call it nonpolar. If it's greater than 0.5, we call it polar. Here are some examples just to see where we've been. If you have 2 of the exact same element, that electronegativity difference is going to be 0, and so we'd call this a nonpolar bond. And if that difference is greater than 0.5, then we'd call this a polar bond. And again, you just have to look these up in the periodic table to see what their electronegativity values are, so long as you have a periodic table that shows you those. You can also see we've put that delta symbol. Delta is that lowercase Greek letter that means partial charge. And partial charge is different than full charge because we're not actually saying that all of the charge of the electron is concentrated on any one element. We're just saying it favors one of these elements. And in particular, it favors fluorine because its electronegativity is so high. So the partial charge is sort of like more of a preference rather than a total charge. But what happens if your molecule is bigger than 2 atoms, right? This is the case for probably most of the molecules that we deal with in chemistry. They're larger than 2 atoms. So how do we understand their polarity, and is it different than just dealing with a single bond? You'll notice that in some of these examples here, there's some polarity going on between the individual atoms, but the shape of the molecule might influence basically how that, that molecule actually experiences any polarity at all. So first, let's look at a case example here. Water on the right and carbon dioxide on the left. Why does water experience polarity? As you can tell, it's got the delta symbols. Why does water experience polarity, but carbon dioxide does not? This is a polar molecule, but carbon dioxide is nonpolar. You might say, well, maybe it doesn't have any polar bonds, but that's not true because carbon and oxygen have an electronegativity difference somewhere around 0.89. That's the difference between those two. But the electronegativity difference between hydrogen and oxygen in water is around 1.3 or so. So we can see that they're both polar and have polar bonds in them. However, the molecules are not. One is polar and one is nonpolar. So in order to figure out how a molecule can be determined as polar or nonpolar, we have to look at 2 things. One, we have to determine whether a molecule has bonds inside of it that are polar. So we have to determine the polarity of those individual bonds, like we just looked at with water and carbon dioxide. We also have to look at the symmetry and shape of the molecule. Symmetry basically means if you kind of cut it in half, what is it a mirror image on the other side, or does it look different? And shape also, of course, means, you know, what does the overall shape of the molecule look like? Often we draw the shape kind of like this little skeleton structure that we've got here. You can tell water has an interesting sort of V shape. But we can also look at this sort of space filling diagram where it's sort of 3D looking, and it kind of has a similar shape to it. So sometimes we have that skeleton structure, and sometimes we have what's called the space filling structure. Well, let's look at the first thing for water, okay? So looking at water, let's look at the polarity of the individual bonds. So from the electronegativity scale, we can get the numbers. Oxygen is 3.44 and hydrogen is 2.1. And there, I said the electronegativity difference earlier is around 1.3, 1.34 to be exact. So is this a polar bond? Yes, definitely a polar bond. And there's a polar bond between this bond and this bond. And what's the direction of that polarity? Well, the oxygen molecule, atom in this molecule is preferring the electrons over the hydrogens. So in each bond, the oxygen wins the battle for the electrons, and so there's a preference for electrons to be around oxygen, so we put that partial charge up there. And there's less of a preference to be around the hydrogen, so we put the partial charge that's positive down there. Now we have to think about the symmetry. So the symmetry of this molecule is that it is a bent shape. So it has this sort of V or bend to it, and that shape, there's a reason for that we don't really investigate in this class totally, but when you look at a shape of a molecule, can you, by that shape, then determine, is this going to be a symmetrical or asymmetrical molecule? Now you might say, well, it is symmetrical. If I cut it down the middle, this side basically folds like that. That's true, but does it have symmetry this way? No, it doesn't, right? The hydrogens are on one side and nothing is on that side. It is not totally symmetrical in this way. So overall, the way that we would say what is going on with the charge here, there's a dipole, which is a fancy word for saying, polarity preference towards one direction. This dipole goes this way towards the oxygen, and there's a negative charge this direction. And if you sum up those dipoles, you get a net dipole going in this direction. That's basically the overall charge to this molecule. Okay, so we've looked at the polarity for water, and we've seen that it is a polar molecule. And now we're going to look at carbon dioxide, which, by the way, it looks very, very similar to water in the fact that water, if you look back at water, its shape has a central atom with two other atoms on the outside, and carbon dioxide has a central atom with two elements on the outside as well, but the shape is different. I hope that's obvious. The polarity, again, we want to look at first, though. Is there a polarity difference between the two? If there's no polarity, then there's not going to be any chance that this molecule can be polar. Well, doesn't meet that. Oxygen is 3.44, carbon is 2.10. The difference is 0.89, that's greater than 0.5, so we'd say yes, this is a polar bond between carbon and oxygen. So these are two polar bonds. However, what's the symmetry like? Well, it's a linear molecule. If it's a linear molecule, this is totally symmetrical. If I cut it this way, if I cut it that way, anyway, it's going to be the same on both sides. It's symmetrical. And because it's symmetrical, we can kind of say that these charges are going to balance out, in a sense, right? They will still, the electrons are going to prefer this oxygen, but they're also going to prefer that oxygen. And in the end, they're kind of going to hover around the entire molecule evenly like this. So just to kind of summarize that, we have polar covalent bonds in carbon dioxide and water, but because water has a bent shape, it is a polar molecule. Because carbon dioxide has a linear shape, it actually is a non-polar molecule. So the shape has to do with it. In this case, methane has a C and an H bond, and the difference between those, which we didn't look into, but the difference between those is less than 0.5. So because it's less than 0.5, we would call the difference here as non-polar. So in the end, it doesn't really matter what shape it has. It's probably not going to make this molecule polar because the bond itself was non-polar. So did you learn that a molecule can be polar or nonpolar even though it has polar bonds within it? Did you learn to determine those bond polarities first and then interpret those based on the shape? We'll practice more with that, but I hope that was a helpful lesson.